Now, I already did an episode on how hard Ford is, and later I realized this is simply not true. Ford is even harder. When writing a program, you always risk making a mistake. And when your program is built and distributed, that mistake will manifest itself as a bug, or a feature if you happen to work for Microsoft. And the beauty of Ford is there are plenty of opportunities to create bugs. Getting a Ford program to compile isn't that hard. Getting a program to run properly, however, is an entirely different story. And yes, it's all got to do with the stack. There's a reason why people embrace local variables, despite the fact that their use is inherently un-Ford-like. Now let's see where you go wrong. Let's do something very simple. Let's do a simple if statement. This word takes a number and prints it when it's odd. It returns nothing. In other words, it consumes the value. Now let's throw a number on the stack and execute question odd dot. The first thing it does is throw 1 on the stack. Then it executes AND and a true flag is left on the stack. That true flag is consumed by if. And then it bombs. Why? Because dot requires a number on the stack, and there is none. We call that stack underflow, or simply the stack is empty. That's fatal, folks. So let's fix this bug and duplicate the value before creating the flag. That should do it. So we throw another number on the stack and try again. We duplicate the value. There's that 1 again. We apply AND and there's our flag. This time it is false. The flag is consumed by if, but we won't enter the conditional. False flag, you get it? Instead, it fails again. But why? There are still values on the stack. And that's exactly the point. We're at the end of the word and there shouldn't be any values left on the stack. But there are. And although this isn't immediately fatal, things will start to go haywire pretty soon, probably resulting in a stack overflow, which means the stack is full. No vacancies, find another motel. This will fix it though. It will remove the value from the stack if there's a false flag residing on that stack. Now, no matter which path you take, the same thing comes out. Nothing. Nada. So remember, never ever create words that can return a different number of stack items. If you do, you just made your life very, very difficult. You're bound to crash and burn because you will have to deal with that every time you call that word. And it's not only plain conditional statements or even data stack errors which can cause problems. Look at this one. It is designed to find 0 values in a 16-element array. It should return the address of the first element that contains a 0 value. Looks fine, huh? Well, it isn't. Let's explain why. So first we throw the address of the array on the stack. We don't know what it is, so let's call it A. Now we throw the loop parameters on the stack, but for simplicity's sake they'll end up on the return stack anyway, so let's put them there. Now let's duplicate that address. Fetch its value, and it happens to be 0, which will result in a true flag. So we will exit and there's a crash.
Brother,
Why? Because there are 2 superfluous items left on the return stack, which will now be treated as valid return values, which there aren't. So the whole system goes haywire in the worst way possible. Yes, you have to be cautious when balancing the data stack, but you have to be even more cautious when balancing the return stack. Now, can we fix that? Yes, we can. This one works. But take my advice, use do loop only if you intend to do the full loop, instead of bailing out halfway, especially if the logic for leaving that loop is complex. It gets ugly pretty quickly, you know. If you're not sure when to leave a loop, you're much better off with a begin repeat or begin until loop, in my humble opinion. Not that these don't have pitfalls, because they have plenty. Now, this is an integer square root routine we did at an earlier episode. And at that moment, there are two values on the stack. Let's name them R and Q. Of course, the while requires a flag, so we have to produce one. And after that while, we'll see our friends again. The flag is consumed and nothing has been added. At this point, we need to change the order of our stack items to Q and R. But right before the repeat, we need to reverse that order again. Why? Because we jump back to begin, where the order was R and Q and not Q and R. And note that you might quit the loop when encountering while. Bonus points if there are multiple points where you can quit the loop. But when you land after a repeat, you better make sure that the same stack diagram is preserved, no matter what comes next. There's also a hidden reason to embrace the stack. It forces you to break up longer words into smaller ones, because if you don't, you're quickly losing track of what's going on. I mean, take an if statement, next another one, and all of a sudden you got 3 paths to check for stack errors. It really adds up. Bugs become impossible to trace at a certain level of nesting, so don't do it. On the other hand, a short, simple word is much easier to track, because there are fewer paths to follow. And if you have tested that word, you can plug it in anywhere else and be assured that it doesn't cause any trouble. That's why words with max and min are so popular with true Ford veterans. You can clip values and ranges without using a whole slew of conditionals. Even better, while you're at it, you might get some clever idea on how to factor it even better, making the codes much more elegant and maintainable. It happens to me all the time. That's good Ford. That's how Ford actually starts to work for you instead of against you. But there's always a but. If you need to allocate multiple values, things might get a bit crowded. And often the most logical thing is to place some values on the return stack. You know, those values that don't change that often. It's quite useful. However, you might have a hard time to refactor those routines, because if you put things on the return stack and call another word, these values are now buried under another return address. Often you're forced to keep things together for that reason, because the only proper solution is to get them back on the data stack, where they end up front, which is often not the most convenient place. Then you have to call another word, return them to the return stack, and invert the whole procedure when you return. Is all that overhead worth it? When designing time-critical programs, it often isn't. And that's why your integer square root routine turned to be out one big blob. So you see, just when you thought Ford was this hard, Ford throws you another curveball. Disaster looms at every single branch you take or make. And I love it. Because it forces you to pay attention. It requires discipline. All those things you need to become not a good but a great programmer. I rarely encounter bugs, even in the most complex and demanding programs, because an error manifests itself pretty quickly. A badly designed program, you simply won't get it to work. Now you can shower yourself in all kinds of safeguards, making even a simple program a painful exercise. Or you can submit to Ford and face the music. Your choice. And ending on that positive note, I'm Hans Beesmer, and this was Back and Forth.